Welcome to This Explainer. Today, we're diving into the absolute backbone of modern computing to really uncover the true purpose of an operating system. Think of your computer's hardware for a second. The processor, the memory, the storage drive. It's kind of like an orchestra of incredibly talented but completely independent musicians. On their own, they have the potential to make beautiful music, but without any coordination, you're just going to get noise. The operating system is that invisible maestro, the conductor making sure everything works together in perfect harmony.
So you got to wonder, what actually stops all your apps from just crashing into each other? It's a pretty fundamental question, right? Without a conductor, a computer is literally just a chaotic jumble of electrical signals and competing hardware components. I mean, if every single application tried to grab the microphone at the exact same time, your system would instantly freeze. This brings us to the core of our exploration today. How does this invisible software layer actually keep everything organized, secure, and running so smoothly?
Here's our roadmap for today. We'll start with the invisible conductor, head inside the kernel, and then look at managing the chaos. From there, we'll cover mastering memory, the virtual memory illusion, and finally, computers inside computers.
Let's kick things off with part 1, the invisible conductor.
Okay, so what exactly does an operating system do? Well, mapping it out visually, you can see it acts as the ultimate manager across 5 main pillars: memory management, file management, security management, hardware management, and process management. Every single time you drag and drop a file, stream a video, or print a document, the OS is quietly working behind the scenes across these 5 areas just to hide the staggering complexity of the hardware from you.
Moving right along to part 2, inside the kernel.
So if the OS is the manager, the kernel is the absolute brain of the operation. It's the central component that has total control over process management, device management, and interrupt handling. When your hardware needs something, or when a software app wants to run a complex calculation, they actually don't talk to each other directly. No way! They talk to the kernel.
Notice how the kernel sits directly in the center here, acting as a vital translator right between your user applications at the top and the physical CPU, memory, and hardware at the bottom. It provides the safe environment for your apps to run, while simultaneously protecting your hardware from malicious or faulty code.
All right, let's jump into part 3, managing the chaos.
We need to understand how the OS keeps all these plates spinning at once without dropping any. Because, let's face it, we all have, 24 browser tabs open while streaming music and downloading files? Here is the secret. Your computer only looks like it's doing everything at the exact same time. In reality, the kernel is overlapping the execution of each process. It uses highly efficient scheduling algorithms to swap tasks in and out of the CPU in literally a fraction of a millisecond. It is a breathtakingly fast juggling act that gives you the illusion of simultaneous processing.
To pull off this multitasking magic, the OS acts as an incredibly strict traffic cop. It uses device drivers to translate data into formats that your specific printer or monitor can actually understand. It sets up buffers and queues to hold data so slower devices can catch up. And crucially, it handles what we call interrupts. These are urgent signals from hardware that temporarily pause the CPU to deal with high-priority tasks. This whole system prevents resources from clashing and crashing.
Let's shift gears to part 4, mastering memory.
The OS has to keep track of literally every single byte of allocated and free memory. Through memory optimization, it actively assigns RAM to apps that need it and reclaims it the second they close. But the absolute most critical function here is memory protection. The OS strictly stops competing applications from trying to use the exact same memory locations at the same time. If it didn't do this, one app overwriting another's data would result in a total system crash.
Which brings us to part 5, the virtual memory illusion.
Now for a really fascinating plot twist. Physical RAM is incredibly fast, but it is heavily limited. So what happens when you open just one too many applications and that physical memory actually runs out? Well, to solve the RAM shortage, the OS uses virtual memory. This is essentially a super clever trick. It combines your fast but limited physical RAM with a designated swap space located on your much slower hard disk drive.
Without virtual memory, you face a catastrophic risk. Take a look at this setup. You have a program trying to run 5 processes, labeled 0 through 4, but the physical RAM only has space for 4 items. So when process 4 tries to access the RAM, there is absolutely no space available for it. The result? Bam! A catastrophic system crash.
To prevent a crash like that, the OS builds the illusion of unlimited memory through a process called in-demand paging.
When the RAM is completely full, the OS identifies the oldest, least used data currently sitting in memory. It temporarily evicts that data, swapping it out to the hard disk. This seamlessly frees up a slot in the physical RAM, allowing the new, urgently needed data to be mapped and executed. It's brilliant.
You can actually see this mechanism in action right here. Notice how process 0 has been kicked out of the RAM and moved over into the hard disk drive. Because process 0 was moved out, process 4 can now safely enter the RAM at location 3. And hey, when process 0 is needed again, the OS will just swap it right back. It's basically a continuous, high-speed shell game.
But while virtual memory is an absolute lifesaver, it comes with a major risk. The hard drive is much, much slower than RAM. If you open too many heavy programs, the OS starts frantically swapping pages in and out of the hard disk just to keep up. This overuse is called disk thrashing. It's that awful moment when your computer crawls to a halt and you hear your hard drive grinding or your fan spinning totally out of control. Your computer is spending all its time just moving data rather than processing it.
Finally, Part 6, Computers Inside Computers. Let's really get into virtual machines. For our final act, we are taking virtualization to the absolute extreme. We aren't just virtualizing memory anymore, we are creating a completely separate, fully functioning computer inside your physical computer. To run a virtual machine, or VM, you need a specialized piece of software called a hypervisor. The hypervisor acts as a master emulation engine. It takes a guest operating system, say a version of Linux, and completely tricks it into believing it's running on its own dedicated physical hardware.
Looking at the entire stack here, you have your physical hardware at the top. But look at that middle layer, the hypervisor. It sits right there, running multiple guest operating systems below it. The hypervisor perfectly isolates these guest systems, meaning guest OS 1 has absolutely no idea guest OS 2 even exists, and neither of them can directly access the physical host without permission.
So, why go through all this trouble? Well, virtual machines are incredibly powerful. Imagine a nuclear power plant running critical software that only works on a 20-year-old operating system. Instead of maintaining ancient, failing hardware, they can run that legacy OS virtually on a modern supercomputer. It also lets developers test dangerous, experimental software. If the virtual machine crashes, the host computer is perfectly safe. Now, the trade-off for sure is a noticeable drop in processing performance and added complexity, but the benefits are massive.
From virtual memory, swapping pages in the blink of an eye, to hypervisors spinning up phantom machines within seconds, it really leaves you wondering just how much of the technology you use daily is actually tangible hardware, and how much is just a brilliant, seamless illusion orchestrated by the operating system. The next time you open an app and it works flawlessly, take a second to appreciate the unbelievable coordination happening right beneath your fingertips. Thanks for joining me on this explainer, and keep questioning how the digital world around you is really built.